When would you use a bidirectional switch in your next design? Maybe you want to replace unidirectional components. Maybe your system has multiple modes and you need some kind of flexibility within those modes. Or maybe you're working on some kind of energy storage, EV, or battery charging design. If any or all of those are the case for you right now, you definitely want to keep on watching this here Chalk Talk. Or maybe you have no idea about what I'm talking about, and then you really need to keep watching. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Eric Persson from Infineon and I explore the benefits of bidirectional switches and the cost and performance specific benefits of Infineon's CoolGaN bidirectional switches. We also explore the applications where these kinds of bidirectional switches would be a good fit, and where GaN bidirectional switch technology is headed in the future. And before we get started, don't forget to click that link. There you can find even more information about this topic from Infineon. Hi, Eric. Thank you so much for joining me.
How are you, Amelia?
I'm great. How are you?
Doing well.
Excellent. All right, so we're talking about Infineon's HV CoolGaN bidirectional transistor today. But Eric, before we get started, what all will we be covering?
Let's start with what is a bidirectional switch, because I think there's some confusion on that topic. So I'll explain that. I'm going to talk about what applications use this bidirectional switch concept today. What are the limitations of using traditional transistor technologies like silicon, IGBTs, even BJT, or silicon carbide. Then we'll talk about how do we make a GaN BDS implementation, because I can also use two discrete GaN devices, as you'll see shortly. But there's a better approach, which is essentially a monolithic device that is smaller and lower cost that makes this a very attractive option. So we'll go over that, the applications that we're seeing trending for the bidirectional switch, and then we'll talk about where the future might take us.
Excellent. Okay, so Eric, before we dig into the details, what exactly is a bidirectional switch?
First of all, let me clarify that there are bidirectional converters, and those could use any kind of switch. Maybe they use a bidirectional switch or not. But the switch itself, if we start on the left-hand side, you can see a conventional FET everyone's familiar with. It only blocks voltage in one direction, in the forward direction. In the reverse direction, there's only two things that can happen. Either it conducts through the body diode, or it conducts through the channel, which can be turned on, which is what we know of as synchronous rectification. So that's it. It's an on-off device, but it only blocks voltage in one direction. On the right-hand side, you can see I've taken two FETs and put them in series. And we call this anti-series because each one is pointing a different direction. In this particular example, I'm showing them connected drain to drain, but you could also do this connecting them source to source. And in this case, I now have two transistors. I can independently turn on or turn off current flow in either direction. So this is a bidirectional switch. It blocks voltage in both directions, and it can conduct current in either direction.
Fantastic. Now, Eric, is it just theory, or are these two transistor AC switch solutions actually being used today? And for what topologies and applications?
Yeah, so I mean, that's a great question. The key is the topology, because you wouldn't just take a bidirectional switch and toss it in anywhere. So let's look at single phase topologies that use the bidirectional switch today. On the left, we've got what is commonly known as a single phase Vienna rectifier. It's in use, it's in practice today. It's not necessarily super popular because you end up with a split bus. So I have plus and minus 400, you can see. And with a single phase input at this power range, typically there's no need to have an 800 volt total bus or even two split 400 volt buses. That's usually, at higher power, let's say. But nevertheless, this is a viable topology that's used today in certain specific applications. On the right-hand side, there's what's called the H4 PFC circuit. It's essentially very much like the Vienna rectifier. You can see it still has L1, it still has the two transistors and the two silicon carbide Schottkys, but notice now, instead of 1200 volt, I'm at 600 volt for the silicon carbide Schottkys. And I have a single 400 volt bus. That's nice. This is much more usable for traditional supplies, but the penalty is I now have an input bridge rectifier. Really only two of them. The lower two are the ones that are the return path. The upper two are mostly for, bypassing inrush current and so on. Nevertheless, this is a popular topology today. It's been shipped in the millions for things like enterprise server power supplies. This is typically used anywhere from 120, US, even 100 volt Japan, up to 230, 240 volt single phase at power levels of, let's say, maybe around a kilowatt up to 3 or so kilowatts, in that range of 1 to 3 kW. This has been a popular topology. One of the nice features of this is that you don't have any worry about shoot through. The switch is either on or off, and there's no way to mess that up. There's no way I can have that switch on and conflicting with another switch that's on. So it's a very simple control strategy.
All right. So, Eric, are you seeing these topologies being used at low power levels or high power levels or both?
Well, yeah, so these are both single phase input, and typically, it kind of depends. If we're talking for a home consumer marketplace, you're limited to whatever 80% of the breaker rating. So in that sort of a setting, you'd never see these over, 1.5 kW maybe. Like I mentioned, in the data centers, maybe up to 3 kW. But now we're seeing the trend in data centers to much higher power levels thanks to the proliferation of AI. And in that case, if we go to the next slide, you can see the three-phase topologies that do use bidirectional switches today. On the left, this is the classic Vienna rectifier, which was originally three-phase. So it's really just three of those that we looked at earlier, the single phase, put together, as it doesn't matter if it's delta or Y connected on the three-phase in. And there's a variant of this known as the T-type rectifier, which can also be an inverter. In this case, on the right, we've taken the 1200 volt silicon carbide Schottkys and replaced them with MOSFETs, 1200 volt SiC. In this case, the SiC can now operate either as a synchronous rectifier to get a little bit higher efficiency if you're only using it as a rectifier, although generally the gain isn't that great. I would say nobody really uses the T-type only for a rectifier. On the other hand, if you want power flow to go the other way, like for a regenerative system, or let's say a big battery system where I want to connect a battery to a utility, a microgrid, and I want power flow to be able to go either direction, then I could use a topology like this. Now I can control those rectifiers and have them on or off whenever I need in order to make power flow go either direction.
Okay, so Eric, does the Vienna only work for single or three phase? What about in the US where we have a lot of split phase 240 volt? Can the topology also be used here?
It's kind of unique to North America. In other parts of the world, they just have single phase or three phase. In the US, we have a lot of what's called split phase, which, technically it is single phase, but it's often treated as two 180-degree out of phase 120 volt. And so you have a 240 volt split phase. And absolutely, in that case, you just take exactly this topology, only get rid of L3 and all of those components, so you have a two-phase system. The difference here is going to be that with either single phase or split phase, you have 100% ripple, meaning that there are periods where the power flow goes to zero every time you have a zero crossing. When you have a three-phase system, you never have that condition. You only have small, like 12 or 15% ripple, and all three phases are contributing power at all times. So that's one of the reasons why at these higher power levels in data centers, they prefer to use now the three-phase input.
Now, these are all hard switching, right? What about soft switching and resonant topologies?
Here, we're looking at a switching condition where we're only turning both switches on or both switches off. There's nothing else going on. There are other topologies like this resonant cycloconverter. This is commonly used today in solar microinverters. You might have seen there was a paper this year at PCIM Europe presented by Enphase Energy that presented exactly this topology. It is also capable of bidirectional power flow. So we see this not only for solar, which is typically, in this case, flowing right to left from the DC side to the AC side, but it can also be used again for battery interface, like for charging up a battery and then discharging it as an AC inverter, for example. What's unique about this topology is that there is no intermediate DC bus. Like in a conventional power supply or inverter system, typically you have the utility side, which is AC to DC. You have a DC link in the middle, and then you have the DC back to AC on the other side. Here, there is no DC link. It's just AC on one side of the transformer, DC on the other. In this case, the bidirectional switches, I'm showing them again configured as two independent switches, but as we'll see, this can be operated in multiple different modes.
So, Eric, this looks really simple, but how can this work with no DC bus in the middle to reduce ripple and store energy for line cycle dropouts?
There's always a compromise with any approach you take. The advantage of this topology is it's simple, it's very efficient because it's resonant, so you don't have switching loss. However, yeah, there's no DC link. But again, this is intended to be used in cases where on the DC side, you have energy storage already, like a battery or something. In that case, I can use the battery itself or whatever the DC load is, that can be essentially the DC link.
Could a topology like this be used for motor drives as well?
There are some converters using what's called, matrix type converter, but really for the bidirectional switch on the next slide, we can see what's called a current source inverter. This is a really unique concept. Now, this is nothing new. This goes back probably almost 100 years using vacuum tubes and so on. The idea here is that it's completely the dual of a voltage source inverter. With a traditional motor drive, it looks somewhat like this. You have 6 switches, but I have a DC bus, as in voltage. I have a fixed voltage bus, and I switch voltage to the motor, and that becomes current then because the motor is inductive. That's known as a voltage source inverter. In a current source inverter, everything is backwards. So the bus could be either polarity, but it's a fixed current going in one direction. Now the switches are essentially just steering that current. One advantage of this is that you notice there are the 3 capacitors by the motor. So with a traditional voltage source inverter, I have extremely high PWM ripple voltage in that connection between the inverter and the motor. That can create problems for the insulation system in the motor because it stresses the insulation because of the high switching ripple voltage. In this case, for the current source inverter, the current into the capacitors gives me a beautiful sine wave voltage driving the motor. So it really helps to eliminate those problems in the motor, like bearing current issues, insulation breakdown, and so on.
So, Eric, this really doesn't look any less complicated than a standard voltage source inverter used for motor drives today. What is the motivation for using this topology? What are the benefits here?
So once again, always a compromise. You do need a current source front end for this that drives the inductor current. As I mentioned, you get sinusoidal voltage to the motor and you eliminate those bearing currents. It's also fault tolerant, meaning that if I have a open or shorted phase, I can still run the machine with reduced performance, kind of for like a limp home mode. So these inverter systems are being looked at for aerospace applications or even automotive where reliability is really critical, and to be able to maintain some level of control over the machine even if you've lost a phase.
Would I have to use the six diodes as shown here, or could I use the two transistor BDS you showed earlier in each switch position and skip the diodes to lower the losses?
The way I've drawn this is really kind of block diagram. This is the function you need. So I don't need a switch in that position. I just need the diode for blocking. But it's a good point. Once again, if I choose to use the two transistor AC switch, then I can synchronously rectify, reduce the losses. So in that sense, yeah, absolutely, this is an application where we would use the bidirectional switch. The only difference is that we wouldn't be using the reverse current conduction capability of that switch. So we do need the bidirectional blocking, but only current going in one direction. So it's not a problem. It's just I'm trying to illustrate it here in a way that makes sense to understand the topology.
So it seems like there are several options for how to make a bidirectional switch using transistors and maybe diodes. Or would I just skip the diodes?
Well, yeah. So let's look at how we configure these two transistor switches because the transistors typically have diodes built into them anyway. So on the next slide, I'll start with, if you remember earlier, I mentioned you could connect drain to drain or source to source. Let's start with the drain to drain connection. So you can see on the left here, I have transistor 1 on top, transistor 2 on the bottom, gate 1, gate 2, and then I have a driver on each of those. So this is an AC switch, and there's a truth table on the right. If you look at the four states I can operate this device, let's begin with both gates off. So in that case, it's just an open switch. I can apply voltage up to its limit in either direction. And if I turn on either G1 or G2, I'm now in what we call diode mode because it behaves like a diode in one direction or the other. It's not until I turn on both gates, now I'm fully on, but notice it says 2R in the table. That's because I have, 1 unit of on resistance contributed from each transistor. So keeping in mind that because I'm making a series connection of two devices, of course, I have twice the RDS on. It's a 4-terminal device. We don't usually bring the drain out. There's no need to. So I have source 1, gate 2, source 2. And I do need 2 separate gate drivers. And I will need 1 or 2 isolated supplies depending on how it's hooked up, where ground is, and so on. But at a minimum, 1, but probably 2 isolated VCC supplies.
So, Eric, I didn't realize that there were not just two, but four operating modes for this combination. Why connect it drain to drain? Wouldn't it be easier to connect this source to source and then the gate drivers could share the same power supply?
Exactly. So on the next slide, I'm showing that source to source connection. And now, because the source is shared, I could choose to, as shown on the left, use a single gate driver and drive both of them. But now I've eliminated that diode mode. It means I can only be either both gates off or both gates on. And of course, it's a 5-terminal device, which if you were going to package this as a discrete package device, means I need another pin for that, but not a big deal. This is actually a common way this device is used. For example, like Vienna rectifier. But again, you can't use diode mode if you need it. On the other hand, on the right-hand side, exactly the same circuit, but I've now added another gate driver. So using the same power supply referenced to the common source, I'm driving G1 and G2 independently. So I need two gate drivers, but only a single isolated VCC supply. And now I have a fully functional bidirectional switch, exactly like we saw on the previous slide where they were drain to drain connected. The difference being that here I could get by with a single isolated supply, whereas with the drain to drain connection, I might need two.
Are there actually three different ways to hook up the transistors and gate drivers? Why wouldn't I just choose the single driver, single supply source to source connection? Wouldn't that be cheaper? Or do I really need the diode mode?
Yeah, great question. Because so far, all I've shown you is like this Vienna rectifier where I don't use the diode mode anyway. So let's look at an example of how this diode mode works. In certain topologies, we use a half bridge of bidirectional switches. And that's what I'm showing on the left. So I have an AC bus now, not a DC bus. And I have an upper transistor Q1, a lower transistor Q2. So if you look at this, you realize this is exactly like the half bridge we use in every other circuit, only instead of a DC bus, this is an AC bus. And that's really a great way to think about how we use this. Imagine this example, and this could be from the resonant converter we looked at previously, the cyclo converter, which uses a half bridge exactly like this. So let's assume in the timing diagram on the right, at the beginning of time, I have Q2 on. So if we start at the top, Q1 G1 is on, Q1 G2 is off, Q2 G1 is on, Q2 G2 is on. So everything's on except Q1 G2. The rationale behind this is that G1 stays on for the entire positive half cycle of the AC line for both transistors. When the AC line's negative, it's G2 for both transistor that stays on the entire time. And if you think about it, with G1 on both transistors, what I really have then is a half bridge, a normal half bridge like we use with a DC link, because G1, the upper is on for both compound switches. So the Q2 is on at the beginning of time, and inductor current, notice it starts out negative from the direction shown with the arrow. I'm conducting, but current is ramping down from the resonant circuit. At T1, I don't wait until zero. I need to have some residual current because that's used to give me my zero voltage switching. So at T1, I switch off. And at this point, essentially both transistors are off. Q1 and Q2 are not conducting anymore, but I still have inductor current. That inductor current is now taking the switch node voltage that you see in a brown color there in the bottom. That voltage is now driven from zero up to the line voltage, and it would keep going, I guess, except that, remember now, Q1 is in diode mode. So the body diode of Q1, the lower half of Q1 now clamps the voltage. And that's where you see the diode drop in that diagram between T2 and T3. This is all happening during the dead time, both switches off, and I'm waiting for the dead time to finish. Then at T3, I turn on Q1 G2. So now the upper transistor is fully on, and the current continues now to the positive half cycle. And I'm essentially synchronously rectifying there. So this is how we use diode mode. It's intended to allow us variability. We don't have to have perfect dead time and know exactly when to turn on the switch in order to get proper control of the voltage.
So, Eric, it looks like the diode mode prevents the situation of an unclamped inductive load, which could result in an overvoltage during dead time.
Yeah, I mean, that's exactly what we're doing. It is possible that if you go back and read the end phase paper, they do actually predictively know when they should switch exactly at the correct time, so they never go into diode conduction mode. But for many applications, that's a pretty significant burden of measurement and control. And usually the dead time is fixed, independent of the current. So during dead time, if I didn't have diode mode, absolutely, I would the voltage on the switch node would just go to infinity, right? And it would kill the devices. So that's exactly what we're doing. We're using it as a catch mode to hold the voltage from going higher or lower than the line, higher than the line or lower than neutral. That way we can prevent an overvoltage situation and not have to have precisely controlled dead time.
And so far, we've been looking at the two transistor version of making a BDS. What about GaN? Is it the same story, or do we need to use two GaN transistors in series to make a bidirectional switch?
I think I mentioned at the beginning that, yeah, we can do this in one transistor. We can also do it with two, but let me wrap up the two transistor approach, and then I'll show you how we do it with one. So what we've just talked about was the three connection and drive configurations possible using two transistors. And these can be, again, bipolar transistors, MOSFETs, IGBTs, or GaN transistors or silicon carbide. Any kind of a normal unidirectional switch can be configured this way, either source to source connected with a single gate driver, source to source connected with two gate drivers, or drain to drain connected. And that gives us, all four operating modes. The source to source connection is most commonly used just because it's simpler and I only need that single isolated supply. For, hard switching topologies like the Vienna rectifier, where I only need on or off, then I would use that simplest approach. On the other hand, for the resonant converters like the cycloconverter, I need that diode mode as we just talked about. But really what drives all this, of course, is cost. And putting two transistors in series becomes an issue. If you think about it, let's say I need a 1 ohm switch, and I take a unidirectional 1 ohm switch. Now I put another one in series with it. Well, now I've got 2 ohms. So I need to start with a twice as big switch. I need a half ohm plus another half ohm to equal 1 ohm. Now, if we go on to the next page, you can see the comparison here between a standard GaN transistor, the gate injection transistor in this case, versus the BDS version of that. So on the left side, the standard GaN, it's a lateral transistor. You have a source on the left-hand side, a gate somewhere in the middle, and a drain on the right. This is our standard GaN GIT. It only blocks in the forward direction, meaning the drain from 0 to positive. If the drain goes negative, this turns back on and becomes, just like any other FET, it conducts in the reverse direction with a diode-like mode. So how do we now make this bidirectional? I can move the drain to the right, and where you see the P-GaN by the drain on the left, I can add another gate. So I've essentially increased the length of the device a little bit, maybe 15%, but now I have a device with two sources, two gates, a little bit higher RDS on, but I can block in both directions. Note that in a standard GIT, the substrate is connected to source. So there's an internal connection that takes care of that. However, when I now have two sources, which one do I connect to? To solve that issue, there is a built-in integrated circuit that connects the substrate to either source 1 or source 2, whichever is lower. It's built in, you don't have to worry about it. The device takes care of itself, but it does take up a little bit of extra die area.
Eric, you mentioned that P-GaN on the drain, and that helps mitigate dynamic RDS on. But in the BDS, there is no drain, just two sources. How do you manage dynamic RDS on here?
Yeah, so the P-GaN, as you say, that's the key for managing, mitigating dynamic RDS on. The gate in the GIT injects holes through that P-GaN, and there's also the P-GaN next to the drain. When we add the second gate, as you say, there is no drain, but I have two gates, both of which can inject holes and mitigate the dynamic RDS on problem. So just to make this clear, a typical Schottky gate GaN device has a dynamic RDS on in the range of, say, 25–30%, meaning that when you first turn it on, it might not be that 1 ohm device. It may be 1.3, and it has a time constant to approach the 1 ohm. With the GIT, because of the PGAN and the hole injection that these offer, that mitigates this dynamic RDS-on issue, and it means that the dynamic RDS-on is really, it's included in the datasheet. It's like 2%. We don't even mention it as a separate line item. It's included in the standard RDS-on spec of the device.
So, Eric, the way it's drawn here, it looks like the BDS is actually a little bit bigger than the unidirectional switch. I thought you mentioned earlier that the BDS is smaller than unidirectional switches.
Right. And this is the challenge to explain. So you're exactly right. This is, I said, what, 15% longer. So when we look at the cross section this way, you can see that the BDS has stretched a bit to accommodate that second gate. But let's now go to comparing the top view. If we start on the left side, I'm showing two unidirectional GaN transistors connected drain to drain. So this would be the approach we talked about at the beginning, where I take two switches, connect them in series, and that's my AC switch. But also, as I mentioned, you need to make the RDS on half for each of those in order that you end up back at the same original RDS on. So I'm showing at the very bottom here 2x plus 2x equals 4x. So if I had my 1 ohm unidirectional switch, I need the area of 4 of those to achieve the same 1 ohm bidirectional switch. So this is the 4x penalty we're talking about. The bidirectional switch, on the other hand, on the right side, yeah, it's a little bit longer, so I have to make the width proportionally a little bit bigger, but it's still much, much smaller than the 4x. Even including the substrate biasing circuit you see underneath the bidirectional switch representation here, instead of 4x, I end up at about 1.5. So comparing those two, if I take the ratio of how much smaller is the bidirectional switch compared to a two-switch implementation of that, it's about a factor of 2.5. That's how we can drive the cost down, and that's what makes this so attractive.
All right, Eric. So this makes sense. So the BDS is really smaller than the two transistor approach because it's essentially a much shorter conduction path for the current in either direction compared to the two transistors in series. Am I getting that right?
Yeah, that's the beauty of this device. I mean, we're essentially taking these two transistors, shoving them together, sharing the same drift region in the drain, and you really can't do that with any other topology. And here's why. If I look at traditional MOSFET, if I look at silicon carbide, if I look at IGBT, they all have vertical current flow. The drain is on the bottom. So in order to try to do a bidirectional switch with any other topology, I now need to figure out how to pattern transistors on both sides of a die and line those up within a couple of microns, submicrons. Very, very challenging. Never say never. Maybe that'll happen someday in the future, but right now, there's nothing else that can create such a small bidirectional switch as GaN.
Sure. So are these real devices that are being used today?
Yeah, so this isn't just a PowerPoint exercise. So I mentioned that the paper at PCIM Europe this year, back in May, that talked about the cycloconverter on the right. That's using GaN going into production now and in high volume. So these are real qualified devices, and we're working with some other customers on AI data center kind of applications using the Vienna rectifier on the left, which we talked about earlier.
Eric, you mentioned bidirectional power flow for the cycloconverter. Is that a result of using the bidirectional switch?
Really, no, it's the topology itself. Remember, I could use a two switch approach here. It doesn't have to be a GaN bidirectional switch. I could use a two switch AC switch, but there are also topologies that have bidirectional power flow that only use unidirectional switches, not even an AC connected two switch approach. Those are separate concepts. Bidirectional power flow can be done with a number of different topologies. In this case, when we say bidirectional, we really just mean the voltage blocking capability of the transistor.
So, Eric, for this single phase cycloconverter, you talked about the high ripple current on the DC side. Could you apply this to a three phase system and that would reduce the ripple current?
We do see this now being targeted for applications like onboard charger. And here's an example of where you could take three of these cycloconverter, put them together as a three-phase system, and I could configure it to accommodate single phase, putting all three in parallel. I could do split phase using two of them, or I can use all three for a three-phase connection. It's very flexible. It doesn't have those DC link capacitors, which are often problematic because of their lifetime in high temperature environment like an automotive. So there's a number of advantages this topology has. And like we talked about earlier, it has a battery on the DC side, so the ripple current isn't a problem.
All right. So, is there any concern about putting GaN BDS right across the line voltage like this? What about lightning strike surge voltage transients? Wouldn't those potentially damage the transistors?
When I first started working with GaN, more than 10 years ago, that was exactly my concern is, man, it's going to be fragile and it's not going to be able to handle any kind of line voltage transient. So there's two things that really mitigate that as a problem. The first thing is that GaN itself doesn't avalanche like a traditional power transistor. So take example of like a 600 volt rated power transistor, a MOSFET. It will avalanche somewhere maybe 680, 690. It turns into like a Zener diode there, which can be good. It depends on the application, but it also means at that point, the voltage can't go any higher and it's now dissipating power in that mode, and it can only do that for a short time. With GaN, it doesn't have a traditional avalanche breakdown. It simply breaks down, but it's at a much higher voltage. For example, a 600 or 650 volt rated GaN device wouldn't break down until 11 or 1200 volts. So they're actually rated right on the data sheet. We say, yeah, that's a 650 volt rated device, but you can temporarily, momentarily, on a pulse duration, go up to 750 or even 850. It's just you have to make sure that the total time spent there over the lifetime of the device is short enough to not impact the total device reliability. The second thing is this topology. Notice again, Q1 and Q2 of the cycloconverter are in series. That means that if they're both off, they form a capacitive voltage divider. So let's say each of these are rated for 600. My line could go to 1200 and Q1 and Q2 would each have 600 across them. So this is a strategy used by solar inverter companies to enable high lightning strike surge voltage capability. Of course, there's still what's not shown here is between the AC line and the inverter, there's always an EMI filter, surge and spike suppression, and so on, as there is in any power supply. But the point being that because of the topology and because of GaN's unique capability to survive high voltage transients, this topology with GaN takes advantage of both of those in a very difficult situation. Rooftop solar is getting hit by lightning all the time. So this is one of the key advantages that we can use with this CoolGaN bidirectional switch.
All right. So, Eric, you said that these are real devices. So, are you selling them now? And how many different types are there?
Before I get to the portfolio, let me just kind of summarize what we talked about here. There are a lot of different topologies using AC switches already in use today, even without GaN. The reason they're being used is because they're efficient, they're single stage, and therefore they can reduce the parts count. AC switches like this, they're commonly made by putting two transistors in series or anti-series. That has the penalty that you're doubling the effective RDS on, and you have to use larger transistors in order to compensate for the fact that you're putting two in series. But despite that, even knowing that, these are still cost-effective topologies being used today in like the Vienna rectifier all the time. Now we introduce this GaN device. It's smaller, lower cost, and it can enable faster switching or higher frequency switching with lower loss. So all of these things make it very attractive for these single stage topologies. Going to higher frequency while maintaining the same losses, or staying at the existing frequency with incredibly low loss. That's the big advantage of these, is to be able to efficiently convert power with the simplest, lowest cost circuit overall. So you'd asked about the reality of these. Let me show you the portfolio as it stands today. There are 4 devices either already on the market or pending release in 2 different packages. Both of these are topside cooled packages, and the RDS on range is from 110 milliohms down to 25. The 55 milliohm is the most advanced part right now. That's going into qualification at a number of customers as we speak. I think you'll only see an expansion of this portfolio as time goes on.
I noticed that they're only shown in surface mount packages. So why not traditional through hole packages like TO247 or similar?
So this is true with all of the GaN that we offer. The reason you're using GaN is because it can switch quickly and therefore provide very low loss. With a traditional package like the through-hole TO247 you mentioned, they're legacy packages that have been used for decades, and customers like them. They're familiar with it, they're happy with it, but they just have too much package inductance to really effectively take advantage of the capability of GaN. They make it difficult to use and difficult to drive. You end up with ringing and overshoot and EMI problems. As a result, we've chosen to go only with surface mount packages because those offer so much better performance with the low inductance. We've also found that making them topside cooled is an even bigger advantage because it allows you to optimize the electrical layout underneath on the PC board for lowest inductance and best performance. And separately, you can optimize the thermal path out away from the board into your heat spreader, heat sink, or whatever you're using.
So, Eric, what about lower voltages like 40 to 100 volts? I don't see those here. So, is it possible to make BDS at lower voltages?
Yeah, absolutely, it is. I figure in the interest of time today, we'd cover only the high voltage. So let's plan on another chalk talk, and we can talk about the 40 to 100 volt, or actually up to 200 volt. It's a different technology, it's a different approach, and I can explain why on the next time.
Great. Okay. So, how do you see this technology evolving and improving in the future?
Yeah, we always look to the roadmaps and where are we going in the future. So one thing for sure, and you see this not only with BDS but with any of the GaN we're making, more integration is coming, and not just because we can do that. It really does simplify the use and the application. So we'll offer logic level PWM inputs with built-in drivers, probably integrated DVDT control. So in hard switching applications like the Vienna rectifier, you can choose. GaN can switch very, very quickly. Maybe I don't want it to switch that quickly because it's causing EMI issue. I can choose to slow it down having DVDT control. We also have the capability of offering a temperature output so that you can keep track of how hot things are getting and maybe adjust the control algorithm to accommodate. And then built-in protection features like short circuit or actually desaturation detection, just 2 different variants of the same thing to protect the device from overcurrent, as well as built-in cycle-by-cycle overcurrent. That way you don't have to rely on alerting the processor then having to do something and shut down and incurring all those delays. It'll just be a built-in OCP that you can then choose to ignore or shut down the system, whatever. As well as over temperature protection. When you reach a critical limit and the temperature output has been ignored, then we can shut down ultimately for safety. And all of this, there's usually a fault reporting pin of some kind. I don't know the specific details, but I'm sure there'll be more coming as these products are finalized and introduced. And finally, the big thing that everyone is really looking forward to is reducing the cost. The goal is we want the GaN devices to be absolutely on par and competitive with silicon. So you have the option to use either device without a cost penalty. The only way we can do that is by going to 300 millimeter wafer fabrication. Infineon has its own internal fabs, so we make these right in Austria. We aren't relying on others' factories that may choose to make them or not for us. This is one of the big advantages we have as Infineon is we own our fabs, and we can drive down the cost by going to these 300 millimeter wafers. That's the future, and I think we should talk again about the low voltage BDS in the future and see where that takes us next.
Fantastic. Let's do that. Well, Eric, I think that's all I have time for today. Thank you so much for joining me.
Yeah, thanks, Amelia. Appreciate the opportunity.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Infineon. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.